Hello everyone, my name is AMMAJI RAO DUPPADA, and in this session we are going to see some proofs against bluntly we are writing some particular integral techniques. So in the last video we have seen how to solve a particular integral in a higher order differential equation. It means part of the solution how we are writing. In that bluntly we follow some techniques. So that techniques you may think like how we need to write this, why we need to write like this only. So in order to understand them, you need to understand some proofs against particular integrals. See, we know, just recap, like complete solution is equal to complementary function plus particular integral. Means complete solution, the whole solution of any system is equal to part of nothing but complementary function and part of nothing but particular integral. In the last video, we have seen particular integral, like some cases we have seen. There are 5 cases. In each case, I told you there is a particular framework to get the solution. So, but the framework is bluntly said. So now the proofs are like this. Let me say proof 1, fundamental like. So what is that? See, for suppose 1 over f of d is operating on x is equal to something. Let us say the answer is some y. Now I just simply say f of d is equal to d. It means 1 over f of d is, I can write d operating on x is equal to y. Now capital X is an input, y is output, right? D I am taking that side, dy. Now operate integration on both sides. Apply integration on both sides. So what you will get, integration of x into dx is equal to integration of dy. D means differentiation only, nothing but integration of dy is y, because differentiation integral will cancel each other. It means y is equal to integration of x into dx. What we need to understand from this is your output y is integration of this x, integration of your input. But in this case, what I am writing f of d is, I said simply simple d, only one time differentiation like. But f of d is function of derivatives. In that case, you need to understand some methods how to operate, or how to dissolve, or how to resolve your function f of d into different forms, so that you can operate on x to get y. So this is what actually proof 1. Now let me say proof 2. We have seen this one also under case 5. Under case 5 we have seen 1 over d minus a operating on capital X is equal to e to the power ax integration of x into e to the power minus ax dx. That's it. It means I told you, if you get like this, in any particular integral, you can write this as an output directly. But how? Now proof is 1 over d minus a is operating on x. Let us say answer is y. So now I have to find y. Y should be equal to this RHS side. Now what I do is capital X into d minus a, I am taking that side, d minus a into y. So capital X is equal to, d means differentiation only, so dy by dx. A is operating on y, nothing but ay. So now my equation is like this, dy by dx minus ay is equal to x. If you see, this equation is linear Leibniz form. First order differential equation we have solved many methods. In that one method we have seen linear Leibniz equation. Okay, linear Leibniz equation. So what is that output is, there we have seen the how to write solution also. The solution is like this. If the equation is looking in this form, dy by dx plus py is equal to q. P comma p and q are functions of x. This is what we call linear Leibniz form. Answer is, direct solution is y into e to the power integration of p into dx is equal to integration of q into e power integration of p into dx plus constant. So this part here, let me close. So y into e power integration of p, how much, dy by dx plus py. P in the place of p we have minus a. It means minus a into dx is equal to integration of q means your x, capital X, nothing but input, e power integration of p into dx minus a into dx. So y into e to the power minus a constant integration of dx is x is equal to integration of x into e to the power minus ax, right, plus constant will be there every time like this. So plus constant. So y is equal to e power minus ax, you bring this side. So e power ax integration of x into e to the power minus ax plus c into e to the power ax. This is anyhow arbitrary constant. This term may exist, may not exist. So your output is now small y is equal to e power ax integration of capital X into e to the power minus ax. So this is what we have seen, or what we have written directly here. 1 over d minus a operating on capital X as an input is equal to, you are getting solution as this. This is the proof against case 5. So now let us see another proof, like for case 1. Case 1, what actually? Your x is e to the power ax. It means 1 over f of d operating on e power ax. What we have written? 1 over f of a into e to the power ax. Like this we are writing. So how we are writing this? The thing is, let me take how we are writing this means, I am taking differentiation on e power ax. What you will get? A into e to the power ax. What I am writing? Differentiation. 2 times differentiation I am doing on e power ax. One time you are getting this. Second time you will get a square into e to the power ax. I am writing 3 times. Differentiation d term I am operating 3 times on e power ax. We will get a cube into e to the power ax. Let me take d cube as f of d operating on e power ax. A power n, right? Any number of times you can do. F of d operating on e power ax 3 times here. So a cube. See, f of d is d cube e power ax. E power ax is not changing. So a cube into e power ax. It means now, okay, here f of d is equal to d cube e power ax. Now a cube I can write like f of a. Right? A cube I can write like f of a, because f of d cube, f of a cube. So f of d operating on e power ax is equal to f of a operating on e power ax. Now you bring f of d this side, f of a this side. It means 1 over f of a e power ax is equal to 1 over f of d e power ax. This is what actually we have written. 1 over f of d operating on e power ax is equal to 1 over f of a into e power ax. That's it. This is the case 1 proof in this way. But remember, here one problem is f of a should not be equal to 0. If f of a is equal to 0, I told you what is the method you have to follow. in solving particular integral cases. Thank you all for watching this video.